Hi, my dear friends. I am Dr. Bharat from Global Academy of Technology. In my previous video session, we had discussed the deflection of beams subjected to point loads and uniformly distributed loads. In today's session, we will discuss the deflection and slope in beams subjected to combined loads, and also we will be discussing about finding the reactions as well as internal forces in the beam elements. Before we go to the session, let us recap the important points in the beams. Beams will have two nodes with 4 degrees of freedom, 2 at each node. There will be 2 translations at node 1 and node 2 and 2 rotations at node 1 and node 2. The stiffness matrix of a beam element is a 4 cross 4 matrix and is given in this equation. The loads in beams are categorized into 2 types: point loads as well as moments, and uniformly distributed loads and uniformly varying loads as another category. The point loads are applied at the nodes as shown in the figure. UDL and UVL is another category of loads that are applied over the entire structure, and the same are given in the following equations. The sign conventions of beam element is as shown in the figure. The upward loads are considered as positive and counterclockwise moments are considered as positive. The following are the supports in the beam elements. The translations is considered 0 for all the supports shown in this figure, including the fixed support, pinned support as well as roller supports, and the beams are allowed to rotate in case of roller supports. The following approach is followed while finding the deflection. Initially, from the given geometric model, a finite element model will be developed. The stiffness matrix of individual element will be determined, and later the global stiffness matrix will be determined for the entire structure. Once the stiffness matrix is determined, the force vectors will be found and the governing equations will be reduced by using elimination approach. Finally, the unknowns will be determined. Let us consider the following example. A cantilever beam shown in the figure is subjected to a uniformly distributed load as well as a point load. A point load of 100 kN is applied at the free end of the beam as well as a uniformly distributed load of 10 kN per meter is applied over the entire structure. The Young's modulus as well as moment of inertia is given in this example. We need to determine the deflection and slope of the beam. Also, we need to find the internal loads. Let us start this problem by converting this geometric model into finite element model. The given geometric model will be converted to finite element model. The finite element model of the structure will be as shown in the figure, which consists of a single element with 4 degrees of freedom. The stiffness matrix can be determined by using this following equation. By substituting the values of length, Young's modulus and moment of inertia in this equation, we will be obtaining the stiffness matrix of this element. The total load in the beam element is the combination of point loads as well as uniformly distributed loads. The point loads are represented as F1, M1, F2 and M2 at the node elements. Since the point load is applied at the free end of the beam, only the component of F2 will be available, whose value will be minus 100 into 10 raised to 3, as the point load is pointing in downward direction. The uniformly distributed load for the beam element is given in this equation, where the value of P in this case will be minus 10 kN per meter and the length will be taken as 4 meters. By substituting these values, the uniformly distributed load will be given as the following values. The total load will be the sum of point loads and uniformly distributed loads. Here the loads will be added because both the loads represent the same element. Therefore, the final load is represented as minus 20 into 10 raised to 3, minus 13.33 into 10 raised to 3, minus 20 into 10 raised to 3 plus minus 100 into 10 raised to 3 put together will be minus 120 into 10 raised to 3 as well as plus 13.33 into 10 raised to 3. The stiffness matrix, displacement equation as well as the force will be arranged in the form of Gaussian equation KQ is equal to F. This Gaussian equation will be reduced by elimination method. In the elimination method, since the first two values of displacement vectors are zeros, the first row as well as first column and second row and second column of the stiffness matrix will be eliminated as shown. The reduced equation will be of this form. By solving this equation, the values of V2 and Pi2 will be determined. The shear force and the bending moments for the structure can be determined and are called as internal loads, which can be determined by multiplying the stiffness matrix and the displacement vectors. Now we have got a stiffness matrix as well as the displacement vectors. By multiplying these two values, we will be able to determine the internal loads. In this example, the internal loads are as follows. The shear force at node 1 as well as bending moment at node 1 are given by these following values, and the shear force at node 2 and bending moment at node 2 are given in these values. The reactions can be obtained by the following equation KQ minus F, where K represents the stiffness matrix, Q represents the displacement vector and F represents the force vectors. The values of R1, R2, R3 and R4 are shown here. Here R1 represents the reaction due to force F1 and R2 represents the reaction due to moment M1 at node 1. Similarly, R3 and R4 represents the reactions due to the force and bending moments at node 2. In this example, we'll be determining the deflection and slope of a fixed beam subjected to moment. A beam of 6 meters length is shown in the figure. At a distance of 4 meters from the left end, a moment of 300 kN is applied in clockwise direction. Also, the value of E into I is given in this example. We'll be also determining the internal loads. Let us start solving this example by converting the geometric model into finite element model. The finite element model will have two elements with 3 nodes. A total of 6 degrees of freedom will be available for the structure. The stiffness matrix will be determined by following equation. By substituting the values of element 1, we will be able to determine the first stiffness matrix for element 1. Also, by substituting the values of element 2, we will be getting the stiffness matrix of element 2. By combining this stiffness matrices, we will be able to obtain the global stiffness matrix. The stiffness matrices will be assembled as shown in the figure, and the empty rows and columns will be substituted with G rows. Therefore, the global stiffness matrix will be obtained as shown in the following equation. This global stiffness matrix will be used to determine the unknowns by substituting in global stiffness equation, or we call it as governing equation. Before finding the governing equation, let us find the displacement vectors as well as force vectors. The displacement vectors as well as the loads for the following example is as shown here. Node 1 and node 3 in this example are fixed. So there are corresponding transverse displacements, and the rotations at node 1 as well as node 3 will be considered as zeros. In this example, we will be determining only the values of V2 and pi2 at node 2. And since there is only moment at node 2, the corresponding M2 value will be minus 300 into 10 raised to 3 Newton meter. The negative sign represents that the applied moment is in clockwise direction. The governing equation is obtained by substituting the stiffness matrix, displacement vectors as well as force matrix in the following equation: KQ equal to F. This equation can be reduced by using elimination method. Here the first row and the first column will be eliminated, second row and second column will be eliminated. Similarly, fifth row and fifth column as well as sixth row and sixth column will be eliminated. The reduced form of the governing equation will be as shown. By solving this equation, we will be determining the values of V2 and pi2. In this numerical, even the internal loads will be found by using the equation K multiplied by Q. Once the value of the inter-stiffness matrix is multiplied with the displacement vector, we will be obtaining the values of the internal forces. The first one represents F1, the internal force applied at node 1. Similarly, the shear force we call it as. Now the bending moment at node 1. Shear force at node 2 will be 0, and bending moment we have some value. F3, the shear force at node 3 as well as bending moment at node 3. These are the shear forces and bending moments. Usually in FEM terms will be called as internal loads. Let us determine the deflection and slope of a fixed beam with combined loading. In this example, we can see that there is a point load as well as a bending moment applied at the center of this structure. Also, the Young's modulus is given, and instead of moment of inertia, the dimensions of the cross sections in mm, that is the width and height of the cross section, are given. Let us find the moment of inertia of the structure by using the formula I is equal to bh cube by 12. The values in mm are converted to meters, and we will be having I is equal to 1.067 into 10 raised to minus 3 meter power 4. Let us now convert the given geometric model into finite element model. The finite element model of the given structure will have two elements with totally 3 nodes. The structure will have 6 degrees of freedom. Let us find the stiffness matrices of individual element by using the following equation. The values of element 1 is as given in this following table, and by substituting these values we will be obtaining the values of first stiffness matrix. Similarly, the values of second element is as given in this table. Now by substituting these values we will be obtaining the next stiffness matrix. By assembling these two stiffness matrix, we will be able to find the global stiffness matrix. The global stiffness matrix for the given example will be as given in this following equation. Before we substitute the global stiffness matrix in the governing equation, let us find the force vectors. Let us find the displacement vectors by applying the boundary conditions. Since it is a fixed beam, node 1 and node 3 has been fixed here. So the displacements at node 1 as well as node 3 will be 0, as well as at node 3 will also be 0. Node 1 as well as node 3 will be 0. The force vectors will be as shown in the figure. Since there is a point load at node 2, F2 will be equal to minus 10 into 10 raised to 3 newtons, and there is a counterclockwise moment applied at node 2 whose value is 20 into 10 raised to 3. With these load vectors and field variables, let us substitute these values in the governing equation and determine the values of V2 and pi2. The governing equation will be as shown in the following figure. By using an elimination approach, the first row and the first column, second row and second column, fifth row and fifth column, and sixth row and sixth column will be eliminated, and the reduced governing equation will be of the form as given in this equation. By solving this equation, we will be able to determine the values of V2 and pi2. Let us find the internal loads. In the previous examples, we have determined the internal load for the entire structure. The internal loads can also be determined by finding the internal loads at each element and later by combining the internal loads. In this example, we will find the internal loads, that is the shear forces and bending moments at each element, and later we will combine these forces to determine the internal loads for the entire structure. The viewers can follow any method of their choice. To find the internal loads for element 1, we will be considering the stiffness matrix of element 1 as well as load vectors of element 1, the displacement vectors of element 1. We will be obtaining the shear forces at node 1, node 2, we will also find the internal loads for element 2 by multiplying the stiffness matrix of second element with the displacement vector of the second element. Thus, we will be applying the shear forces and bending moments at node 2 as well as node 3. By combining these forces, we will be able to determine the internal loads of the entire structure. The first 4 represents the internal loads of the first element, where F1, M1, F2, M2. The later next 4 represents the internal loads of the second element, F2, M2, F3 and M3. The viewers once again are reminded here, the internal loads are nothing but the shear forces and bending moments. So the final internal loads will be obtained by combining the internal loads of individual elements and is as given in this following values. Let us discuss another example of finding deflection and slope of the beam subjected to the following load conditions. In this example, the beam is subjected to both uniformly distributed load as well as uniformly varying load. The uniformly distributed load is of 1 kN per meter over the span of 2 meters, and uniformly varying load is of 1.5 kN per meter over the span of the remaining half. The value of Young's modulus as well as moment of inertia is given in this example. Also, there is a pinned support at the left side as well as a roller support on the right end of the beam. Let us start this numerical by converting the finite element model. The finite element model of the structure will have 2 elements and a total of 6 degrees of freedom. The stiffness matrix will be obtained by using the following equation. By using the values of element 1 and substituting these values in the stiffness matrix, we will be able to obtain the stiffness matrix of the first element. Similarly, by substituting the values as shown in this table in the stiffness matrix equation, we will be able to determine the values of second stiffness matrix. By assembling the stiffness matrices, we will be determining the global stiffness matrix. The global stiffness matrix of this structure will be given in this equation. This will be the global stiffness matrix, and this stiffness matrix will be used to determine the unknowns. Let us find the loads in that structure. In this structure, there is a combination of uniformly distributed load as well as uniformly varying load. At element 1, there is a uniformly distributed load whose equation will be given by PL by 2, PL square by 12, PL by 2 as well as minus PL square by 12. In this example, the value of P will be minus 1000 Newton per meter and the value of L will be 2 meters. By substituting these values, we will get the uniformly distributed load force vector as represented in this equation. Similarly, we will try to find the uniformly varying load at second element. The equation to determine uniformly varying load force vector is represented as shown in the figure. In this case, the value of P is minus 1500 Newton per meter and length will be 2 meters. By substituting these values, we will be able to get the value of uniformly varying load force vector. Since there are 2 different elements, the values will be assembled. The total load will be the combination of uniformly distributed load as well as uniformly varying load. So the final load vector for the structure given will be minus 1000, minus 333.34. These are the 2 values at node 1, minus 2050 newtons and 33.34 at node 2, as well as minus 450 newtons and 200 Newton meter at node 3. By using this load vectors, we will be able to determine the field variables. The field variables in the structure are represented in this following equation. Since it is a pinned support at node 1, the corresponding displacement and slope are considered as 0. At node 2, it is free to move. Therefore, the values of transverse displacement as well as slope are allowed at node 2. At node 3, since it is a roller support, the vertical displacement is restricted. Therefore, the value of vertical displacement will be 0 and the beam is allowed to rotate. Therefore, the value of pi 3 will be available. So, in this example, we will be determining the value of V2, value of pi 2 as well as value of pi 3. The force vectors which we have already determined is represented in this equation. Substituting all these equations in governing equation, will be able to determine the value of V2, pi 2 as well as pi 3. The governing equation will be as represented in this following equation. By using elimination approach, the first row and the first column, second row and the second column, fifth row and the fifth column of the stiffness matrix will be eliminated, and the reduced governing equation will be given in this form. By solving this equation, we will be able to determine the values of V2, pi 2 and pi 3, which are represented in these values. The viewers are advised to go through this numerical example once again and see how the force vectors can be determined. The most important part in solving a numerical in beams is determining the force vectors. Remaining all the other process will be simple. Let us solve one more example to find how the force vectors will influence the entire numerical. Let us solve one more example to determine the deflection and slope of the beam subjected to the loads as shown in the figure. In this problem, a beam is subjected to a combination of uniformly distributed load as well as uniformly varying load. At the same time, there is a point load applied at the center of this element. The Young's modulus and moment of inertia of this numerical in this example has also been given. Let us start this problem by converting the geometric model into finite element. This structure will have two elements, element 1 and element 2, and totally will have 6 degrees of freedom. Let us find the stiffness matrix of each element. By substituting these values of L1, E1 and I1 in this equation, we will be able to determine the stiffness matrix of the first element. Similarly, by substituting these values of L2, E2 and I2, we will be able to determine the stiffness matrix of the second element. Let us now combine the stiffness matrices to obtain the global stiffness matrix. By assembling the stiffness matrices, we will be getting the global stiffness matrix as represented in this equation. Now, the most important step is to determine the force vectors. Let us properly observe the structure. The element 1 has two types of loads. It has got a UDL of 5 kilonewton meter, and above on the top of the UDL there is also a UVL of 5 kilonewton meter. So both UDL and UVL are applied at element 1 itself. Let us find the values of force vectors due to UDL and UVL, and later we will add these two values to obtain the values of uniformly distributed load at element 1. The uniformly distributed load at element 1 will be given in this equation, whose value of P is minus 5000 Newton per meter and length is 1 meter. By substituting these values in this equation, we will get the uniformly distributed load. Let us also find the uniformly varying load at element 1. The equation for uniformly varying load is as shown here. In this case, the value of P is minus 5000 Newton per meter and the value of length will be 2 meters. By substituting the value of P and L, we will be able to determine the values of UVL. So, we have obtained the values of uniformly distributed load and uniformly varying load at element 1. The total load vectors at element 1 will be obtained by adding the uniformly varying loads and uniformly distributed loads. Therefore, the total distributed load at element 1 will be adding this both values since they are acting at the same elements. Once you add it, this will be the load vector of distributed load vector at element 1. Let us also find the distributed load vector of the entire structure. To find the distributed load vectors of the entire structure, we will also try to determine the distributed load at element 2. Since you see on the screen there is no load at element 2, I mean to say there is no distributed load at element 2. Therefore, the distributed load at element 2 will be equal to 0. So, by assembling this total distributed loads at element 1, which is given in this equation, and element 2, which are zeros, will be able to determine the total load vector due to distributed load at element 1. Therefore, the total load vector, okay, it will be UDL as well as the combination of UVL will be equal to minus 4250 minus 666.67. These two represent at node 1, later minus 3250 newtons and 583.34 Newton meter at node 2, and at node 3 it will be zeros. This will be the total distributed load of the entire structure. Now at the same time, this structure as also called as also have a moment. Now let us find the moment. So there are point loads and moments are also there on the entire structure. We can also, this is second category of the loads. The structure has also have a moment at node 2. Therefore, finding the entire load vector due to point or moments will be equal to the following equation. So F1, there is no load, point load at node 1. There will be no moment at node 1. Now coming back to node 2, there is no point load, but there is a moment in counterclockwise direction. So it is taken as plus 20 into 10 raised to 3 Newton meter. And F3, there is no point load, and M3, there is no moment at node 3. By combining these values, the total load on the structure is the combination of distributed loads as well as the point and moments. Now here, by simply adding these two values, because these two represent the same structure, will be determining the final loads. These are the final loads on the entire structure, and these loads will be used to determine the field variables. The field variables in the structure are as shown in this expression. Since they are the pinned structures, the corresponding transverse displacements at node 1 and also at node 3 will be zeros, and also the slopes at node 1 and node 3 will be 0. And this will be the values of the force vectors. By using these values in the governing equation, we will be able to determine the values of V2 and pi 2. The governing equation will be reduced by applying the concept of elimination approach. First row and first column. Similarly, second row and second column. Fifth row and fifth column, as well as sixth row and sixth column will be eliminated, and the reduced governing equation will be of this form. By solving this equation, we will be able to determine the values of V2 and pi 2. So in this example, most important which we need to consider is determining the force vectors. In this example, the force vectors are considered for the entire structure, and use this force vectors in governing equation to obtain the values of V2 and pi 2. So that's all in this video session. I once again request all the viewers. I request all the viewers to go through my previous sessions on solving the numericals as well as finding the deflection and slope of the beam elements and carefully determine the load vectors. The load vectors is crucial in solving the numericals or determining the deflection and slope in beam elements. Thank you.